Okay, let's start with our next session. I'm happy to introduce you our next speaker, Dmitry Budker, professor at the University of California, Berkeley, and Helmholtz Institute in Mainz, right? And he will tell us about many ways to explore fundamental questions or how big is your table.
Yeah.
Okay, thank you.
Thank you so much. Thank you so much for the invitation. It's very nice to be here and give a talk, especially because there are probably no cold atoms in my talk, essentially. So I'm very happy anyways to be here. And I do have a scientific part, which is, yeah, and the whole talk is scientific, but there's a more specific scientific part that follows. But I'd like to start by saying some very trivial things, but I hope that they will be useful anyway. So I want to start with the question, how big is your table? And I will explain what it means, especially if I can, now this doesn't work either. Let's see. Okay, now it's working, great. So we have, as physicists, a lot to be proud of. So there's, for example, a beautiful theory of quantum electrodynamics, and we can calculate certain things from first principles to, I don't know, 12 or more significant digits. Then we go to the lab, we measure them, and there's nice agreement. And then in more applied directions, for instance, the previous talk by Professor Cornish demonstrated the degree of sophistication with which we can control atoms and molecules and do wonderful things with them. So there's a lot to be proud of, but this shouldn't obscure the fact that physics is in deep, what's the longer word, trouble these days, because there are many things we don't really know. And one example here is observations seem to indicate that 80% of matter in the universe is dark matter business, and nobody knows exactly what it is. And you know, so basically, you can say we have an idea, but only 1/5 of matter in the universe. Another problem is there's a lot of matter around us, but very little antimatter, and the properties between matter and antimatter are symmetric. So what was the reason for this imbalance? It's another problem, and there is actually a list of maybe a dozen of very gross. No, it's not a small problem; it's a huge problem of this sort. And another thought that is sort of from a different direction, but these two things will come together, is that today physics gets very specialized, as you know. And so, for instance, if you take a high energy physicist working on collisions and an atomic physicist, they cannot often find common language. Even I'm supposed to be a card-carrying atomic physicist, and I go to some atomic physics talk. I have real hard, I confess to you, a real hard time understanding what my colleagues are saying. This doesn't hold for the previous talk. That was right. but oftentimes I find, oh my God, what is this about? And I think this trend is understandable because, you know, these areas are all reaching great degree of sophistication, but there is also, I think, something bad about it. But luckily, there is an opposite trend in this, and it has to do with a wonderful tradition that originated in atomic physics, that doing some precise tabletop experiments, you can actually try to address these big questions, address these big problems. And it starts maybe with experiments of measuring parity violation in atoms that help establish the standard model. And more recently, these are dark matter searches with tabletop experiments. And now if you take an experiment like this, okay, that is a tabletop dark matter search. I'll tell you about some of these in a minute. This is an experiment with atoms and molecules. So it's AMO physics, atomic, molecular, and optical physics. Some experiments use, for instance, color centers in diamond. They're almost like atomic. So there's condensed matter. But if you're measuring, for instance, parity violation, or even looking for dark matter, you also have to say that this is nuclear physics and also particle physics, because dark matter presumably consists of some particles, and so you are doing the particle physics on the tabletop. But also, if you're really catching the dark matter that is present in the galaxy, it's also observational astronomy. So all of a sudden, you have these all fields of physics coming together, and you can say that it's sort of a new. Okay, guys, I'm going to take this off. Okay. If you want, this is like a new renaissance. When we say Renaissance man, right? It's somebody or a woman. It's somebody who does science, writes poetry. So there's something like this, right? So we have all of the fields of physics coming together, and I find that amazing. And this tabletop mentality is a certain way of doing physics. It's usually it's a relatively small experiment with a relatively small team. So if you have a new idea in the evening or at night, you can come in the morning, you can change something in the apparatus, you can test that. And it's very hard to do if you are in another style of science, like accelerator experiments. 30 years for accelerator based physics is the scale on which things develop. So it's kind of hard. But this idea of being agile, multidisciplinary, I feel it penetrates, give some examples, into high energy physics, for example, as well. And I find this very, very nice. So my answer, as a result, to the question that I posed, how big is your tabletop, is as big as you want it to be. And specifically, I would say this goes from nanoscale. So, for instance, my colleagues in China currently are doing a lot of very beautiful experiments where they use nitrogen vacancy centers to look for exotic fifth force interaction between particles on the nanoscale. And this is a way to look for particles that could be dark matter particles, etc. And so their tabletop is nanoscale. Then there is the optical table, like I started with, atomic parity violation, fifth force measurements on a centimeter to meter scale, dark matter searches. Then there are these famous electric dipole moment experiments. Electric dipole moment of a particle is forbidden by both parity and time reversal symmetry. So it's a CP violating effect, and it's a wonderful way to look for new physics. These experiments used to be tabletop. Now many of them are growing and becoming more like a room size experiment, nevertheless compact. Then there are accelerator based experiments. You all heard about, for instance, the precision measurement of the magnetic moment of the muon, G-2 experiments. Absolutely stunningly beautiful experiments with anti-hydrogen. So people make anti-hydrogen at CERN, and now do precision spectroscopy of anti-hydrogen. This eventually will reach the precision comparable to hydrogen. And it's a relatively small experiment, but if you forget that there is an accelerator attached to it to produce the anti-protons over there. But then even bigger machines, so I'm involved in this proposal called the Gamma Factory. And this idea here is that you take this big Large Hadron Collider and you reconfigure it in some ways to make it into a fantastic tunable source of gamma rays with energies up to 400 mega electron volt. Now, if you heard the previous talk, right, then you saw that the key is laser manipulation, stir up this and that. So you now have an idea, then you find the appropriate lasers, you pay the bills to the companies to get them, and then you can do absolutely anything you want with any atom or molecule. But if we go to nuclei, we can't do this because we don't have lasers that work there. So the idea of this gamma factory, it's not really a laser, but it's in that sort of direction to have a tunable source with which we can drive potentially nuclear transitions, and not only in exotic nuclei like thorium, about which we'll hear, or someone who will be here tomorrow, Professor Pike, but any kind of nuclei. And 400 MeV is even higher than the nuclear scale. Right, so we're going up in scale from nanoscale. We're already to the size of big accelerator. Let's make the next step. So there are some dark matter search experiments now that are the size of the Earth. So for instance, I'm involved in this global network of optical magnetometers for exotic physics search, is known. And what it is a sensitive atomic magnetometer put actually inside a magnetic shield. So the real magnetic field doesn't affect it, but dark matter presumably can penetrate the shield. And we put dozens of them around the globe, and we take the data in a correlated fashion. Then this is like a big detector, now the Earth size, okay? And there's also a nice collaboration that does the same with atomic clocks, actually kind of ancient atomic clocks on board of the GPS system. It's called GPS.dm. So we take the data from those clocks and analyze them. So now we are to the size of the Earth. Now people are going out in space, and there will be gravitational detectors in space. So now we are to the size maybe comparable to the solar system. And then you can continue this, and finally you get to people who study cosmic microwave background, and you can say, if their mind is agile, we can say that their tabletop is the size of the universe. Okay, so it's all sizes. I hope I made my point. And with this, now my duty to the tabletop physics is paid, and now I'm going to tell you about the actual tabletop experiments that are, just one example, essentially, of how you look for dark matter on a table. And yes, I'm going to repeat myself by showing you the cover of our book called Physics on Your Feet, with some fun problems for the PhD exams that used to be given at Berkeley, abandoned PhD oral PhD exams some years ago, but the book remains. And here's an elephant, and that's an elephant in the room. So just saying that it's a huge problem in your face. Again, 80% of matter seems to be something that we don't know. And English language, that's a good thing to say here in Great Britain, is a very funny thing, because sometimes people say, we have no idea what dark matter is. And by this, they mean that we don't know what dark matter is. But it does not mean that we have no ideas what it is. We have, in fact, a long list of ideas about what it might be. Okay, and there is just a partial list, and it will take probably several hours to go over each of these points in detail. So I'm going to skip this, and I'm going to tell you that there is sort of a general category of dark matter that is that's drawing more and more attention. So it used to be the time when people thought that dark matter must be something that's called a WIMP, weakly interactive massive particle. So it's basically a particle similar in mass to common particles like a proton or a neutron, GeV kind of energy, or maybe like a Higgs, like 100 GeV or something like that. And all you need from this particle is that it doesn't really interact by strong or electromagnetic interaction. Only interacts with the strength of the weak interactions. Nothing particularly strange from the point of view of particle physics. And then it fits amazingly, fits like a glove, so to say. You can produce it in the early universe and with the right abundance, and it explains everything. The only problem with it that people have been looking and sort of narrowing the parameter space for these WIMPs, and they can't find them. And then people started thinking more, well, maybe it's something else. Maybe it's not the WIMP. And in recent years, this particular class of dark matter that's called ultralight bosonic dark matter is becoming very popular. So what do we mean by ultralight, and why do all of a sudden we know the spin? Something about the spin, right? Bosonic means the spin is integer. So what's the connection? And it turns out it's actually a funny thing. So imagine that the galaxy is a box, okay, and then you start putting particles, dark matter particles, into the box, okay. Now, by looking at the rotation curves, the speeds of the stars in the galaxy, we can actually measure the density of dark matter here, and it comes to be about 0.3, 0.4 GeV per cubic centimeter. That means it's like 1 proton per 3 cubic centimeter. And this is like, what, I don't know, 10 to the 22 proton per cubic centimeter, something like that. So it seems like a very small number, but because the galaxy is so sparse, if you stick so many particles in it, it's dominant mass in the galaxy. Okay, so now let's assume for simplicity that dark matter consists of one type of particles, right? So if you say, okay, 0.3 GeV per cubic centimeter, and my particle is, say, 1 EV. So you immediately divide 0.3 GeV by 1 EV, and you get, 0.3 times 10 to the 9 particles per cubic centimeter, right? So you can immediately find the density. So now the galaxy is a box, and you start putting these particles in. And imagine that these particles are fermions, okay? Then we all did it, I think, in the first year of quantum mechanics, and the context we did it in is electron gas in a metal. Because your piece of metal is a box, and then you put your electrons there, and the fermions, they follow Fermi-Dirac distribution. And if you remember, this idea is that they cannot occupy the same quantum state, that the only thing they can do is start moving fast to increase their phase space. And so you have this Fermi-Dirac distribution, and there is this Fermi velocity. So now you can assume that the particle has a certain mass and that the universe is a box. Then you can, in one line, calculate the Fermi speed, Fermi velocity. And if you say that dark matter is associated with the galaxy, it better be that the Fermi velocity is smaller than the escape velocity from the galaxy, right? And the escape velocity from the galaxy is about 10 to minus 3 c, 10 to minus 3 of the speed of light. So if you put the numbers in, you see that if a particle is lighter than a few electron volts, it cannot be a fermion. So that's why we say ultralight bosonic dark matter. Beautiful. Then there is a huge variety of candidates here. There is, for instance, the most popular candidate here is an axion. It's a spin 0 particle with odd intrinsic parity. And the reason this is a popular candidate is because it was actually introduced long before people thought of it as a dark matter candidate. It was introduced to explain another puzzle, which is why strong interactions do not violate CP symmetry. So strong interactions are described by quantum chromodynamics, and it's very easy to put theoretically CP violation to quantum chromodynamics, and it's not there. And so this also some people say, well, it is what it is, but other people are very uncomfortable for it accidentally being zero. And so the axions were introduced as particles that explain very naturally why strong interactions respect CP. And then people realized also that they could be a very good dark matter candidate. And somehow the more problems a new particle solves, the more motivated it is, right? I think I buy this philosophy. Kill all the birds with one stone, as they say. Okay, and so among these candidates, there is also this. Do you see the cursor there? Oh, yes, good. So maybe I can even make it into. Okay. Laser pointer, yeah. So there is also a spin zero, but even intrinsic parity particles, and they have different names. One of them is dilaton, for example, and there's many other names for this. And these are the ones we're going to talk about at the moment. But before I tell you a little bit of the story, how this developed, I just need to say one more general thing. That or actually a couple general things. So if you have a lot of bosons around, you can think, of course, of them as particles, like photons, for example, or bosons, and you can. But there are many contexts where you don't want to think about them as particles, but you can think about them as a field. So if you take a plain capacitor, you apply positive voltage here, negative voltage here. There is electric field. You can think about this as some kind of photons of zero frequency, but it's not convenient for most problems. Right? They think about the field. So we're going to think about such a field, classical field, if you want, for this kind of dark matter. And this field is described by proper equations. And there's a Klein-Gordon equation that describes the scalars, and the Klein-Gordon equation tells us that you can't have a static field. Okay, it has to oscillate in time, just like photon at a certain energy, has to oscillate in the light field. And in this case, for a finite mass particle, the oscillation frequency has to be close to Compton frequency. What is the Compton frequency? The math, so mc squared is the energy, you say equal to h bar omega or h nu, and this nu is the Compton frequency. So basically is the same as the mass. Good. And second thing is that as I will explain a little bit in further slides, the effect of this scalar field is to effectively change the value of fundamental constants. Change the value of fundamental, for instance, alpha, or the mass of electron, or something like this. And we will use this. But now the time has come for me to tell you, the story, maybe in an interesting perspective. So this is Asimina Arvanitaki. She is a professor of physics at the Perimeter Institute and a very well-known theorist in particle physics and dark matter. And it was in 2014 that Mina and her students here have published a proposal. They're saying, okay, if dark matter consists of these dilatons, these scalar particles, they affect fundamental constants. The fundamental constants should oscillate. And when they oscillate, if you think about it, take an atomic energy level. It depends, for example, on alpha. Okay, and then if alpha changes, then the energy should also be changing. So why don't we, and by the way, this depends on the specific atomic state. So let's take an atomic clock state, and measure how it's what's happening with respect to another atomic clock. So let's do a clock comparison, and this way try to look for this oscillation of fundamental constants. And that was very interesting. And a PhD student in my group, Nathan Leifer, he read that preprint, and he came to me and said, "I have an idea." Okay, so we can immediately do this. What Professor Vanitaki is proposing, and we don't even need to do an experiment because we have already data on tape. And indeed, for many years before that, and until today, we're working a lot with this amazing atom called dysprosium. And what's special about dysprosium is that it has there are many things. Okay, in cold atoms now, dysprosium is very popular because it's the atom with the largest magnetic moment, I believe, in the ground state. So people do Bose-Einstein condensation, all kinds of things. By the way, our group was the first to laser cool dysprosium. Maybe not known widely. Anyway, it has also two excited states of opposite parity that are very, very close together. So if you look at different isotopic or hyperfine components, you have energies splitting, which is, goes from like 3 megahertz to a few gigahertz. It's even much smaller than the famous small splitting in 2s to p states in hydrogen. And because these are opposite parity levels, you can derive directly an electric dipole transition between these states, and you can measure the energy difference between them directly. So you can think about it as a differential atomic clock, if you like. So think about this transition, optical transition, as one clock, and this as another clock, and so you can do clock comparison, not by taking two precise numbers and comparing them, but measuring the difference directly, which in some cases is very beneficial. And so what we've been doing actually for many years. So for instance, we were trying to look for slow drifts on the time scales of the lifetime of the universe. Then for it's like maybe some people at some point came up with evidence from astrophysics that maybe the value of alpha in the early universe was part in 10 to the 5 different from what it is today. And then if you divide by the lifetime of the universe and assume a linear drift, then you have 10 to minus 15 or something per year. So we were looking for this. We also looked at the dependence of alpha on the gravitational potential, Lorentz invariance, test parity values, whatnot. So it's been a laboratory for all kinds of precision experiments, but we have never looked for oscillations. And what Nathan Leifer proposed is that let's take our existing data that's already on disk and analyze it for oscillations. And we were able to do it very, very quickly. And we had several data sets. So in one data set was about, on the order of 1 day. That's one particular date. And the other one was on the order of a month. And we analyzed it for oscillations and were able to immediately set rather stringent limits on the parameters for this dilaton. So I would like to maybe explain this kind of plot that you see here. It's a typical thing that dark matter hunters do. So they plot on the horizontal axis the mass, in this case it's the logarithm of the mass of the particle, and on top you see the Compton frequency, and on the vertical axis is the coupling strength. So how much the presence of the field affects the fundamental constants. And so we obtained these limits. By the way, 10⁻² electron volt is a very interesting number. This corresponds to the Compton oscillation frequency on the order of a year. Okay, and very slow on human scale. This is actually, you cannot have dark matter lighter than this. Why? Because then the de Broglie wavelengths will be bigger than the galaxy, and we started with the statement that dark matter has to be within the galaxy. So, what an interesting result. And these were the guys who carried out the analysis. This is Nathan Leifer, the hero of the story, I would say. And we published it. And in this paper, it was, you know, what I call a couch experiment. I love this. When you don't actually need to do a new experiment, and maybe not even new theory, you just have an idea, you sit on the couch, you scribble something, and you get new result from it. So we did this. It took us several months of data analysis, but it's still a couch experiment. And that we in the paper we said that when serious people get to work on this with atomic clocks and frequency cone comparison and whatnot, they can do much better. And so that's what we predicted is going to happen. And this happened very quickly. And I should say that currently the clock people, including the group of Professor Pike here, have done like we predicted and much better actually than this. So, but this was the beginning. So yeah, and one more thing before I move on with my story is I'm so actually inspired by this idea of couch experiments and reusing the data that you have, that I recruited my colleague Andrei Derivenko, who is the spokesperson for this GPS.dm collaboration, and we wrote a pamphlet that we published in Physics Today that calls for everybody doing precision measurement to please date and position stamp their data and store it. The storage is not very expensive. Who knows, maybe you're going to be writing a lot of PRLs, a few years from now when new ideas come what to do with the data. Yeah. Right, but moving on with the story. These are my very dear theory friends. So the first three people is Professor Peter Graham at Stanford, and then it's David Kaplan and Surjit Rajendran at the Johns Hopkins University, and they got a breakthrough prize not so long ago for their theories of a particle called the relaxion. And I love it because it's a play. I love play on words. Okay, and you remember the axion, a strong candidate for dark matter. So they have hypothesized that this relaxion undergoes relaxation oscillations in the early universe. And so this axion undergoing relaxation oscillations is a relaxion. And the reason they thought it was an interesting thing to consider, because now in addition to solving the CP, strong CP problem, dark matter problem, it could also solve the hierarchy problem. And the problem, there are many ways to formulate the hierarchy problem, but one of them is, as we already discussed, particles have masses below, on the order of 100 GeV, and the natural scales of the universe are 10 to the 16. That's the so-called grand unification energy, where strengths of different interactions come together, or 10 to the 19 GeV. It's the Planck energy, where where gravitation has to be quantum. So you have 10 to the 16, 10 to the 19, and 100 GeV. So you have 14, 15, 16 orders of magnitude discrepancy, and we are kind of used for things being on the order of 1. Yeah, we feel uncomfortable when they are not on the order of 1. So this is called the hierarchy problem. For why is there such disparity of scale? And these relaxions apparently explain this very nicely. Now, another friend of mine, Gilad Perez at the Weizmann Institute, he took this idea and worked some more on it and gave it his own flavor, and this resulted in a large number of papers. I'm not going to bore you with describing everything, but I just will mention a few highlights about Gilad's relaxions. First of all, his relaxion is a mixed state in terms of parity. So it is both a scalar and a pseudoscalar. And I already said that scalars, they are sort of the manifestation is the change of fundamental constants or apparent change of fundamental constants. And it turns out that pseudoscalars interact completely differently. They actually affect the spins of standard model particles, and so you can look for them with magnetometers. Because Gilad's relaxion is at the same time a scalar and a pseudoscalar, you can look for it both with atomic clocks and magnetometers. And for many years, I was calling on people to make hybrid networks that have all kinds of sensors in the magnetometers and clocks, and in particular, and people were saying, well, why do you want that? This is different. What is the advantage? This theory all of a sudden motivates what I have been calling for many years, because now you can say, okay, we're looking for relaxion, so that does make sense to combine these different types of sensors. And if we detect something with this hybrid network, we immediately can say it's a relaxion and not something else. That's one thing. The other thing is that it was in conjunction with this relaxion, but actually it applies to any kind of ultralight dark matter. Gilad's group has considered possible enhancement of the local density of dark matter in the presence of the Earth or the Sun, and they for some reason invited me to join them on this work. So there's a series of publications about the possible enhancements near the Earth and the Sun, and we'll come back to it. The most important point on this slide that I want to mention is that Gilad somehow came up with his favorite range of possible masses, or what the mass of his relaxion could be. And you see here that he likes 10 to minus 10 to 10 to minus 3 electron volt. Now, you are all students of atomic physics, so you all know that 1 electron volt is about 2 times 10 to the 14 hertz. Yeah, you know that? And if we multiply by 10 to minus 10, we get 20 kilohertz. And now this brings a little bit of a problem, because if you want to look for these things with atomic clocks, you find that your good clocks, best clocks, are not fast enough. Because Eckert will correct me, but if an atomic clock gives you a reading once per second, it's considered a fast clock, right? More or less these days. And here you need to do much faster. So what do you do? All right, and so we started thinking about how we can get at this problem, and in particular with this gentleman who is now a professor in Crete. We came up with an idea of how to do this, and we were actually stunned because our idea seemed to be so trivial that there are 2 possibilities in my mind. Either we were completely wrong, something was deeply wrong with this idea, or maybe people are already doing it. So we were very worried about it. So we called another friend at the Weizmann Institute, Professor Roy Ozeri, and we were able to convince him that the idea is good. And nobody knew that it would work or not. And so we decided that it's so simple that we can do it over the weekend, and we call it the Weekend Relaxion Search Laboratory, or RESL experiment. Okay, it didn't work for the weekend, it worked for a few months, but it was very fast. And we did what we thought about, and this may look a bit complicated, but in fact, if you ever did an undergraduate laser spectroscopy laboratory, you did this as a saturation spectroscopy. experiment. It's a bit of a fancy saturation spectroscopy here. It's called polarization spectroscopy. But you send two beams counter propagating to eliminate the Doppler. And the idea is very simple. So again, you have the atomic energy level, and now it oscillates fast. And then you take a laser and you lock it to something stable, a Budker cavity, for example. And then if there is oscillation like this, you should be able to detect the oscillation on your signal. So this is our first result. We even found some dark matter here. And it turned out to be radio interference. Took us a little bit to eliminate that candidate. And so the first attempt was at the level of a few times 10 to minus 15 of delta F over F. We published that. I was, before it was published, I still was very, very scared that they're so simple that something must be wrong, but maybe not. And then we did an improved version. I'm going very fast because the chairperson says I have 2 minutes to go. Okay, and now if you look at this, we are pushing with very simple experiment the level of 10 to minus 18. So it's close to what the clocks do, and the reason we can get away with such high resolution is because we look for high frequency oscillation. So a lot of problems with slow drifts and so on are not existent here. Anyway, so this is all good. Then if you do atomic experiments, you are not sensitive to nuclear mass. So in order to address that, we did also molecular experiments in cooperation also with Professor Stefan Schiller at Düsseldorf. We did iodine experiments. Then I don't have time to tell you about these other things. I'm going to skip that. One thing I want to mention that there is this recent work, and this is actually in collaboration with the department of Professor Pike at PTB, and the heroes here are Melina and Niels, and this is actually now not a fast clock, but one of these fancy ytterbium ion clocks. And the special thing about this particular experiment is that it's sensitive to variation of nuclear size due to dark matter. Okay, the last point before I come to the conclusion that I want to make is that, remember I mentioned that there is a possible enhancement of the density, local density of dark matter by several orders of magnitude, actually, in the vicinity of something heavy like the sun. And recently, people have started to send spacecraft to the sun. There is the famous Parker space probe, and then India recently also launched a probe that's just like a Parker probe. And so there are proposals that people are publishing about putting atomic clocks onto such Parker-like missions to send to the sun. And I think it's a very good idea, but I would like to extend this idea. And in addition to the clock, or maybe as part of it, you see, anytime you lock the laser, you have a saturation spectroscopy thing. Why don't we also analyze this? It could be done very cheaply for these fast oscillations. And then we can directly probe the enhancement near the sun. And with this, I'm out of time. So the key points, if you like, is that the scalar dark matter mimics oscillations of fundamental constants. The first experiments were done with dysprosium, and they are continuing, and now are also done with advanced clocks at PTB, for example. If you want to go to higher frequencies, you can do relatively simple experiments with atoms and molecules, and they are pushing delta F over F 10 to minus 18 or something like this. I think it's pretty decent. And the frequencies, so far, we worked up to 100 megahertz. And now we are pushing it with my colleagues towards the 1 gigahertz. There's some electronic development that needs to be done. And the last point is that maybe we can do these searches on spacecraft going to the sun to directly probe the over densities near the sun. And with this, I'd like to thank you for your attention.
Very much for your talk. Let's process a bit. If maybe someone has a question. Yes, please.
Very nice talk. So you told you use Klein-Gordon equation to model the dilatones, like, and you told the fundamental constants change. So what sort of interaction terms do you have?
I have, this is a theory question that's above my pay grade, but I may have here. So these are more of my theory friends. People always say, if you have scalar dark matter, it changes the fundamental constants. But is it obvious? No, it's not obvious. Okay, so what you need to do is you have to go to the standard model Lagrangian, and you have to write in the terms of possible interaction. That was not done by me, but by Gilad mostly. And then you stare at them and you see, aha, somehow it looks like you can rewrite them in such a way as fundamental constant change. But this is an effective, it's like a shortcut if you want.
Okay, so this is like an RG flow, like a renormalizing.
What's RG?
Like if you put like an energy cutoff, like at different energies, we have different fundamental constants, right? When we
Yes.
normalization group flow.
Yeah. I probably, but one point that I didn't have time to make is kind of interesting, maybe general. Maybe if I can have 1 minute for that. So in the business of varying of fundamental constants, Eckert and I were drilled by theories for many years that we are not allowed to talk about variation of constants with dimensions. Okay, so we can only talk about variation of dimensionless constants, and this goes to this whole problem that if you're measuring something with a ruler and you see some change, so what is changing? Is it your object is changing or your ruler is changing? Always there's ambiguity. But if you have dimensionless constants, that's not a problem. And also that people always say you can talk about variation of alpha, but not variation of V. You can talk about variation of mass of electron to mass of a proton, but not. So that's good. This is a very good suggestion by the theory. But we point out in this paper with these guys that it's something very, very trivial. So if you are considering oscillations on the scale that's faster than the duration of your experiment, then you can always normalize by average value, the spontaneous value by average value. And so in that respect, you can say, okay, it is really the variation of mass of an electron or electric charge. And you can also trace this statement back to the Lagrangian. So if you have fast oscillations, it's okay to talk about variation of dimension constants. Yeah.
We usually don't have time for more questions. You can approach Dmitry in the coffee break. Okay, let's